A stopper on a string of negligible mass rotates in a horizontal circle of radius 0.2 meters with an unknown angular speed. If the stopper revolves at 64 radians per second, when the radius is reduced by half, what is the initial angular speed of the stopper? So here, this is a stopper, rubber stopper, and you can rotate it around something like this. It's rotating, and when you change the radius, you change the angular speed. So here's a larger radius. If I reduce the radius, the angular speed becomes faster. Conservation of angular momentum. In this example, when we calculate the moment of inertia, we take that rubber stopper just to be a point particle. And the momentum, the moment of inertia is going to be the mass of the rubber stopper times radius squared, where radius is distance from the point of rotation or the axis of rotation to the location of the rubber stopper. Okay. Okay, let's draw a picture. So this is the axis of rotation. And the rubber, there's a string and a rubber stopper like that. And the rubber stopper is rotating around this axis. It's coming into and out of the board like that. It's going in a circle. Now let's look at the forces on this rubber stopper. First of all, there's the force of gravity. And then there's some tension. Now, do you think these forces are going to make an external torque acting on the particle? The tension is not going to have an external torque because it goes right through towards the center of, towards the axis of rotation. So it does not make a torque. But force of gravity does have a torque. There's an external torque with the force of gravity because it's at 90 degrees with the radius vector. So it is an external torque. Also, in this situation, there's just one force going down. So the rubber stopper is going to just go to the ground. So if there's an external torque, we can't say that angular momentum is conserved. Or what can we do? What is the problem with this? What do we do to make it work? Who knows? How can we make this thing work? Well, the string is not horizontal. It can't be horizontal. So we have to have some force acting upwards to keep the thing from falling down. So let's take off this. String is not like that. String is actually like this. It's at an angle. And now we have a component of the tension in the vertical direction. And so tension vertical. So tension vertical and force of gravity have the same magnitude, but opposite directions. So the net force in the vertical direction is 0. By the way, this is the tension. It looks like this. It has a component. That's the vertical component. So net force in the vertical direction is 0. That means there's no torque caused by these vertical forces. So with no external torque, we can say that angular momentum is conserved. So now we can work it out. What do we have here? So initially, we got radius R1, which is 0.2 meters. And that's going to change. R2 was R1 over 2, which is 0.1 meters. And omega 2 is 64 radians per second. And omega 1 is what we don't know. That's what we're trying to find. Now let's look at the moment of inertia. So I1 is just m R1 squared. And I2 is m R2 squared. We just consider this stopper to be a point particle, which is at a distance of R1 or R2 from the axis of rotation. So L1 equals L2. Momentum is conserved. Therefore, I1 omega 1 equals I2 omega 2. Now let's put in what the i's are. So we have m R1 squared omega 1 equals m R2 squared omega 2. We want to find omega 1. So let's solve for omega 1. The m's cancel out. R2 over R1 squared times omega 2. R2 is R1 over 2. So let's put that into here. R1 over 2 divided by R1 squared times omega 2. This thing is just, R1's cancel. It's just 1 over 2 squared. So it's 1/4 omega 2, which is 1/4 times 64, which is 16 radians per second. So that is our answer. Notice I never had to substitute in the actual value of R1 and R2. I just used the symbols. The R1s cancel out, so I didn't need to even know what it was. The vertical tension equals, yes, the tension, the component of tension, the vertical direction, has the same magnitude as the force of gravity downwards. And in that case, then the thing is not going to have any vertical acceleration. So it will remain in one plane as it goes around.